Hi, welcome back to this channel. In this video, we are continue to 3.2. In the previous video, we learned how to write the Nernst equation and also the reaction quotient in the Nernst equation. Then we also try to calculate the cell potential by using the Nernst equation. So we will only apply the Nernst equation at the non-standard condition. So in this video, we are going to focus on explain the factors that will affect the cell potential, and then we are going to look for the tutorial question which will cover to determine the concentration of the partial pressure of a species, and also calculate the equilibrium constant when E cell equal to 0. For this donkey, predict the spontaneity of a cell. So as we already know, if the E cell potential is equal to positive value, the reaction is spontaneous. Hi, in this slide, we are going to discuss the factors that will affect the value of the cell potential. So basically, if we look at end of this part, we want to know what should we do so that the cell potential will be increased. So the first factor that we consider is the temperature. So as we know, if the temperature is decreasing, this value RT over NF basically also will be decreased. Basically also will be decreased. Okay, so once this one is decreased, the E0 cell minus a smaller value, so will cause the E cell increase. So this is the first factor that we consider. Okay, next one here is mentioned about concentration of product. So we know that concentration of product will be appear in the reaction quotient. So as we also know, reaction quotient stands for concentration of product over concentration of reactants. So if the concentration of the product is decreasing and the concentration is reactant is remain, so overall we know that the Q value will be decreased. So when the Q value decrease, the ln Q also will decrease, and then it will cause the E cell increase mathematically. Next one, we will look at the concentration of the reactant. So at here we say that concentration of reactant increase. So again, if the Q equal to concentration of product over concentration of reactant. So now means that concentration of product remain, but the concentration of reactant is increased. So because we are over a value which is large value or bigger value, this will cause the Q decreasing. So again, once the Q decreasing, the ln Q will decrease. So E0 cell is a fixed value minus a smaller value, so the E cell will be increased. So by combining these two ideas, so we also come out, if the reaction quotient is decreasing, so the E cell also will be increased. So the one which mentioned over here, which is the partial pressure of the gas. So basically, the partial pressure of the gas will be considered similar for the concentration. During the operation of a galvanic cell, as we already know that electron always flow from anode to cathode, where is A to C, which we always mention in the class. So then we also know that oxidation happens at the anode. So for example, anode undergo oxidation. So it's a metal will going to form metal ion by losing certain amount of electron. So from this half equation, then we know that the concentration of the product is increasing. Then now we look at the cathode. Cathode reaction happen at the cathode is the reduction. So let's say we have another metal. So for this case, the metal ion For example, N plus, okay, the N ion will going to gain certain amount of the electron and form metal N. So based on this half equation, we know that concentration of reactant is decreasing. Okay, so this is what mentioned in the statement here, will resulting in product formation increase and a decrease in the reactant concentration. So when this happens, the Q value, as we know that Q equal to concentration of product over concentration of reactant. So concentration of product is getting higher while the concentration of reactant is getting lower. So a bigger value divided with a smaller value, we will notice that the Q value will be increased. So when the Q value increase, means that log Q also will be increased. So once the log Q increase, we compare with the Nernst equation, E cell equal to E naught cell minus 0.0592 over N log Q. So when the log Q value is increased, these whole things also will be increased. So E naught cell minus a bigger value, so the E cell will be decreased. So this is the explanation over here. Then next we will look at here. So when the cell potential is decreasing, it will reach the equilibrium at one moment. So at the equilibrium means that there is no transfer of the electron. So then there is no electron moving, the E cell will equal to 0. And then at the same time now, because already achieved equilibrium, the reaction quotient will be replaced by the symbol of K, which is represent the equilibrium constant. Now let's proceed with the tutorial question 13, which involve how to determine the equilibrium constant. So we start with question A. The cell potential for the galvanic cell below is 2.299 volt. Okay, because of the concentration given here is 0.04 molar and also 0.005 molar. So we know that this is at the non-standard condition. Therefore, the 2.299 volt here basically is represent E cell. Then the question asks us to write the half equation at anode, cathode, and overall equation. So this is the cell notation, and we know that cell notation always as simple as A, B, C. So means that zinc is the anode and will undergo oxidation. So zinc lose 2 electrons, becomes zinc 2 plus at the anode, while for the cathode, the S2 gas gain electron to produce X minus. This is the reaction at the anode. However, this equation, the number of mole of electron is not balanced. So basically, this whole half equation at the cathode, we need to times 2. So 1 times 2, 2 more electron, and then will become 1 more of X2 and 2 more of X minus. Then 2 more of electron can be cancelled out. End up, the overall reaction for the product side have zinc solid, X2 gas. While for the product side, we have zinc 2 plus aqueous and also 2X minus aqueous. So again, for the reminder, when we write the balanced chemical equation, we no need to include the concentration is okay. Still in question 13, but now we are looking at 13b. Without referring to the SRP table, calculate the standard electrode potential for the X2 and X negative. So we know that this is the cathode, and then we are given the E cell, means that we are going to solve this problem using the Nernst equation. Okay, so Nernst equation is E cell equal to E naught cell minus 0.0592 over N log Q. So when you notice of this, the product in this case is the zinc 2 plus, and then X negative is the product. And then we always mention that for the reaction quotient, we will going to include the species in the aqueous state and also the gas state. So from here we know that we will not include the zinc, but we need to include the pressure of the X2. So that's why we put a partial pressure of X2. So by substitute the value 0.04 for zinc 2 plus, 0.005 for X negative, and that is with the power of 2 based on the overall equation. Partial pressure of the hydrogen is 1, and then the coefficient for X2 in the equation also 1, so 1 to the power of 1. So if you didn't write out, this one is still okay. So then by press the calculator, we will notice that E naught cell will equal to positive 2.12 volt. And then here given us the E naught for the anode. So by using the formula E naught cathode minus E naught anode, so we will able to get the answer 2.12 minus 0.76, so equal to positive 1.36. So if you refer to the SRP value, you will notice basically the X actually is referred to the chlorine gas. Continue with question C. Determine the equilibrium constant of the reaction. So as the previous slide we already mentioned, if we want to determine the equilibrium constant, means that it is referred to K. So K means that already achieved equilibrium. So at equilibrium, E cell will equal to 0 and Q will equal to Kc. So when we do like this, we will say that E cell equal to 0, E naught cell minus 0.0592 over 2. Okay, so from here we can determine the value of the E naught cell. So, or basically we do it from here first. E naught cell will equal to 0.0592 over 2 log K. So what is the value of the E naught cell? So E naught cell is equal to E naught cathode minus E naught anode, kakak tolak adik. So from here we know that the kakak is the chlorine gas, which is positive 1.36, and then minus the zinc is the adik, is negative 0.76 equal to 0.0592 over 2, or basically you already press the calculator, it will equal to 0.0296 log K. So 2.12 equal to 0.0296 log K. So from here then you will do 2.12 over 0.0296 equal to log K. Okay, then you anti-log the K, you will get the answer for the K is 4.18 exponent 10 to the power of 71. Okay, let's proceed to the last tutorial question in the 3.2 Nernst equation, which is question 11. So when we look at this diagram, normally we will think that the left-hand side is the anode, while the right-hand side is the cathode. But when we go through the question, you will notice that they give us the redox reaction occurs in the figure 1 is this. So from here we can see that copper turns to copper 2 plus. So from here we notice that the oxidation number from 0 to positive 2, at where we know that once the oxidation number increase, this is a oxidation process. So when this is oxidation process, means that copper is the anode. So what we justify or what we identify just now is incorrect. Always remember that you need to justify the anode and cathode not based on the diagram but based on the information given in the questions. So then next for the question A, they ask us to write the half-cell equation for the redox reaction. So if the question asks us write the half-cell equation, basically means that you need to identify which is anode and which is cathode, which we already identified just now. So anode is the copper. So copper lose 2 electrons will become copper 2 plus. While then the remaining species will involve in the reduction process. So 2 more of MnO4 negative equals 8 more of H plus, 2 more of MnO2 and 4 more of H2O. So but then later you need to balance this one with the number of mole of electron. So MO4 negative is with the oxidation number -1. So 2 times -1 plus 8 times positive 1. And then equal 2 to the power of 0 plus 4 to the power 4 multiplied with 0. So we basically know that positive 6 is more positive. So we will balance it by adding the charge we will balance the charge by adding electron at more positive side. So it means that x equal to -6. So this is why here we have 6 more of electrons. Okay, then we go to part B, identify the oxidizing agent and reducing agent. To keep in mind that if the question asks us to look for, no matter it's oxidizing agent or reducing agent, basically it is referred to reactant. So as we know, oxidizing agent is the species which will undergo reduction. So reduction happens at the cathode. So when we look at the cathode here, the reagent is the MnO4 negative. Reducing agent undergo oxidation. So oxidation happens at the anode. So refer to the anode here. You will see that the reactant at the anode is copper. So the reducing agent is copper. Last question, which is about the reaction coefficient Q. So reaction coefficient Q, we can refer to the overall equation at where is concentration of product over concentration of reactants. So based on the equation here, concentration of product we have aqueous is Cu2 plus and then with the coefficient 3, so to the power of 3. Then over concentration NaO4 to the power of 2 because here we have the 2 as the coefficient, and then H plus also is the aqueous form, so we have to include it with the power of 8. So this is the reaction quotient. Continue with 11 donkey. Based on the given standard reduction potential, determine the E0 cell. Means that we want to determine the cell potential at standard condition. So we're going to use the formula takat tolak adik E0 cathode minus E0 anode. So at the same time, we also can double confirm that positive 1.51 is more positive. So the more positive SRP value will be the cathode. Okay, so means that what we identify at the previous slide is correct based on the overall equation. So if the manganese will be MnO4 negative become the cathode, so means that the copper will automatically become the anode. So just substitute in the value E0 cell equal to E0 cathode minus E0 anode. plus 1.51 minus 0.34, so the answer will be 1.17, at where the reaction is spontaneous since the E naught cell is equal to positive value. So done for donkey. Then next we need to calculate the potential of the cell when the concentration is 0.2, 0.03 and the concentration of H plus is 0.1. So from here basically we will know that we need to find the E cell. So means that we are going to use the Nernst equation. So the formula for the Nernst equation, is E cell equal to E naught cell minus 0.0592 over N. So based on the half equation in the previous slide, we will notice that the number of mole of electron involved is 6. Then the reaction quotient in part C can be bring forward here. Okay, so then now you just substitute the value in. Cu2 plus is 0.03 molar, so it's correct. And then MnO4 negative is 0.2 to the power of 2. While the concentration H plus is 0.1 to the power of 8. Press the calculator, so you will notice that the E cell will equal to positive 1.07 volt, and then this reaction is still spontaneous because the E cell value is equal to positive. Last question, briefly describe the changes in cell potential if the pH of the electrolyte in the cathode half cell is rise. So as we know, pH is equal to negative log concentration H plus. So if the pH value is increased, so basically the concentration of H plus is reduced based on this formula. So this causes the value of log Q to be increased. Okay, so concentration H plus is reduced, so overall others value is maintained, but H plus is reducing. So means that the Q value will be increased. So E naught cell minus log Q with a higher value, so it will cause the E cell decreasing. So we already finished for chapter 3.2. So in next video, we are going to continue with the last part of this chapter, which is cover the electrolytic cell. So see you in next video. Thank you. Bye-bye.